So in this section, we're going to extend what we learned from the last section, and we're going to, instead of 2 equations and 2 variables, now we'll have 3 or more equations and 3 or more variables. So this is where the new stuff starts. Nonetheless, the logic and method of solving these are the same, and we're going to start out with more word problems. So first, you identify the variables, and second, you formulate equations, and each resource of demand gets an equation, and then you solve. Let's go and look at an example. Dairy Queen makes 3 kinds of ice cream using milk, cream, vanilla, and cocoa. Each gallon of deluxe vanilla uses 2 quarts of milk, 2 quarts of cream, and 3 ounces of vanilla. Each gallon of vanilla uses 3 quarts of milk, 1 quart of cream, and 2 ounces of vanilla. And each deluxe chocolate uses 3.5 quarts of milk, 0.5 quarts of cream, and 5 ounces of cocoa. The shop has on hand 150 gallons of milk, 66 gallons of cream, 20 pounds of vanilla, and 35 pounds of cocoa. So how many gallons of each type of ice cream should be made for the shop to use up all of these ingredients? So again, these problems are really, really long, and it's going to be hard and confusing if you don't try to break it down in steps. So again, here's our first step: to identify the variables. We look at the last sentence, which says how many gallons of each type of ice cream should the shop make. And so we know each type of ice cream is our variable. And we know that there's deluxe vanilla, regular vanilla, and deluxe chocolate. So here I have assigned X, Y, and Z to be gallons of each of the ice cream made. Now we proceed to formulate the equations. And remember, again, each resource will get its own equation. Here we have milk, cream, vanilla, and cocoa for our 4 resources. So we set up the table. Each resource gets its own equation. Put the resources on the side here. Put the variables on top. Set it equal to what you have. And now you just fill in the table. So deluxe vanilla, which is X, use 2 quarts of milk, so here's 2X. 2 quarts of cream, 2X for cream. 3 ounces of vanilla, 3X for vanilla. It doesn't use any cocoa, so it's going to be 0X for the cocoa equation. And for the same way, you fill the rest: 3Y milk, 1Y cream, 2Y vanilla, and again 0Y cocoa, and Z 3.5 Z milk, 0.5 Z cream, and 5Z cocoa. Here with what you have on hand, they kind of try to trick you a little bit, and you will definitely see this on web work and probably the test. Here, what we have on hand and what we're using up are in different units. So you must convert the units such that they match. So here with milk, this is given in quarts when you use it up, and what we have on hand is gallon. So we have to multiply how many gallons we have by 4 to know how many quarts we have. So here, what you have on hand in milk equation is the number of quarts you have. In the same way, for cream, we have gallons of cream multiplied by 4 to find out how many quarts of cream we have. And here, pounds of vanilla and pounds of cocoa, we have to multiply them by 16 to find out how many ounces of each we have, since it's given to us in ounces when we use it up. So now we're going to try to solve it. Solving a system of more than 2 equations and more than 2 variables is pretty complicated. And we're not actually going to solve this right now. But Instead, we're going to learn a new method called the row reduction. So you might have learned in high school what a matrix is. A matrix simply is just a bunch of numbers in a rectangular form put inside brackets like this. So here we're going to represent a system of equation into an augmented matrix form. And augmented simply means that beside the x, y, and z, here we also have the numbers on the right. So it's augmented. Here to represent the equations into matrix form is the easiest thing you would do. So you just put 2 for 2x, and then 3 for 3y, 3.5 for 3.5z, and then 632 over here. And for each equation, do the same. So basically, this is the x column, this is the y column, and this is the z column, and this is your constant column. So the idea of a row reduction is to manipulate the matrix such that it will eventually look like this. And we want it to look like this because this is the x column, so we have 1x, and then 0y, 0z to become a. So here we have x equals a, y equals b, and z equals c. So if we can reduce the matrix into looking like this, we have effectively solved for x, y, and z. But before we actually get into how to reduce the matrix to look like this, we're going to learn about this thing called a leading one. So a leading one has to satisfy two conditions in order for it to be a leading one. First, it has to be a first non-zero number in the row that is 1. And it also has to lie in a column full of zeros. So let's look at this circled one here. This is an example of a leading one because it is the first non-zero number in this row because this is 0, and then next time is a 1. So this one is the first non-zero number. And it also is in the column full of zeros because if you look down the column only has zeros in it. So this is a leading one. Here's a couple of examples of what was not a leading one. So here, this one does not satisfy the second condition, which it does not lie in a column full of zeros because you can see the column here. This is a 2 instead of a 0. And here, this one doesn't satisfy because this is not the first non-zero number. It has the 2 preceding it in the row. So a matrix is considered reduced if every row has a leading one. So let's look at this matrix. This is a row reduction. This is a reduced matrix because here we have a leading one for the first row. This is a leading one with a column full of zeros. And here we have a leading one for the second row because this is the first one with a column full of zeros. And the last row also has a leading one with this one full of zeros. Here's another example of a reduced matrix. And here you can see, so this is a leading one for the first row. Second row has a leading one. And the third row also has a leading one. Notice that it didn't matter that some columns have non-zeros because the only thing that's important is that each row has a leading one. So here's an example of a non-reduced matrix. Here you can see the row 1 and row 3 has a leading one, but row 2 doesn't. Because this one does not qualify to be a leading one because it does not lie in a column full of zeros because this 2 is here. So how we're going to reduce a matrix is we're going to try to get a leading one in each row, so that's the objective. And here are the three operations we're going to use in order to achieve that. We can switch rows. We can multiply row by a constant, so you can multiply row by a 3 throughout the entire equation. Or you can add and subtract two rows and replace one of them with a new row. And now we're going to go through how to use these operations to row reduce. So first I want to point out that my method might be slightly or drastically different than what your professor is going to show you. Our logic is going to be the same, but our way of working it out might be quite different. Personally, I think my way is probably better than your professor's way, but nevertheless, you choose which way suits you the most and which way you understand it better. So now let's row reduce. Again, I want to say this is one of the hardest things you're going to need to learn in Finite. So make sure you understand everything from this section so far right now. So the idea of a leading one. And if you don't, go review the material from before this point. So make sure you understand the idea of a leading one and what it means for a matrix to be reduced. And after you go through this reduction method, don't worry about it if you don't get it the first time. Simply rewatch it and try to understand each step, why I do them, and what it accomplishes. Here we're going to use this system as an example. So first step, just put it in augmented matrix form. So first we're going to get a leading one for row 1. And we do that by making the corner a 1 here. Since it actually already is a 1, so we skip that. We don't have to do anything about it. So let's say if it was not a 1, let's say if it was a 2, then you can just divide the whole row by 2 in order to make it a 1. So now we have to clear the column, because for this 1 to be a leading 1, it has to be in a column full of zeros. So we're going to make this 5 and this negative 2 to become a 0. So we do that by manipulating row 1. So we're going to multiply row 1 by something and then add it to these rows in order to cancel out the 5 and the negative 2. So here I'm going to multiply row 1 by negative 5. And notice I have put the negative 5 times row 1 right next to row 2. A very easy mistake to make is to write down negative 5 times row 1 and start multiplying row 2 by negative 5. I purposefully chose to write down negative 5 times row 1 right next to row 2 because afterward, when we add, it's much simpler. So just make sure you don't make the mistake of multiplying the wrong rows. So here I have in blue to make sure I have emphasized the point that we're multiplying negative 5 times row 1. So anyway, here is what negative 5 times row 1 is, which is negative 5, negative 15, positive 10, and negative 10. And I've multiplied row 1 by negative 5 because in order to cancel out this 5 plus negative 5 will be 0. So that's why I used the negative of whatever this number is in order to accomplish my purpose of clearing the column, which is making these numbers 0. So in the same step, I'm going to try to clear this negative 2 as well by multiplying row 1 by positive 2, the negative of this number. And so, again, we're multiplying row 1 and putting it right next to row 3. So 2 times row 1 is 2, 6, negative 4, and positive 4. So here, the fact that I've put the multiplied row next to these rows now I simply add side by side. So again, the row, we're trying to get a leading one for row 1. So that means that the row 1 is going to be the row that stays the same throughout this particular step. Because or else the 1 is going to change. We don't want the 1 to change. So that's why row 1 doesn't change in the step. Also, that is also the row we're manipulating, because the row that's being manipulated won't change throughout the step. So here row 1 is going to stay the exact same. And then row 2 is going to be replaced by the sum of the old row 2 and the negative 5 times row 1. So here we simply add side by side. So 5 plus negative 5 is 0. 16 plus negative 15 is 1. Negative 8 plus 10 is 2. And 19 plus negative 10 is 9. So here we have a new row 2 with a 0 here, which accomplishes exactly what we were trying to satisfy, which is getting this to be a leading one by clearing the column, making these zeros. So by the same logic, row 3 is going to work out the same way, adding side by side the old row 3 and a row 1 times positive 2. So we have negative 2 plus 2 is 0, negative 2 plus 6 is 4, 13 plus negative 4 is 9, and 35 plus 4 is 39. So now we have accomplished exactly what we set out to do, which was getting leading 1 for row 1. So now we're going to move on to row 2. And we're going to do the exact same thing as we just did to make this a leading 1. So we have to make this a 1, but it already is, so we don't have to do anything. So now we again are going to clear the column, making this 3 and 4 go away. So again, we're trying to get a leading 1 for row 2. So row 2 is being manipulated, and row 2 is going to stay the same throughout this step. So I manipulate row 2 by multiplying by negative 3 to get rid of this 3 over here. Again, we are multiplying row 2 and we put it right next to row 1 because we want to eliminate the old row 1. But we don't want to make the mistake of multiplying row 1 again. So here I've highlighted, we're multiplying negative 3 times row 2. So in the same way, I want to try to get rid of this 4. I multiply row 2 by negative 4. And now, row 2 stays the same, and old row 1 goes away by changing into a new row 1, which is adding these two side by side. So 1 and 0 is 1, 3 negative 3 is 0, negative 2 and negative 6 is negative 8, and 2 and negative 27 is negative 25. And again, the same way for row 3. 0 and 0 is 0, 4 and negative 4 is 0, 9 negative 8 is 1, 39 negative 36 is 3. So now we have achieved getting leading 1 for row 2. So here we got a 1, and then a column full of zeros. Now, again, we'll repeat the exact same thing we did for row 1 and row 2 for row 3. So row 3 stay the same, and we manipulate row 3. So to get rid of this 8, we multiply row 3 by 8. And to get rid of this 2, we multiply row 3 by negative 2. Put it right next to row 1 and row 2. Now we add side by side. So now this 8 and 2, negative 8 and 2 also goes away. And now we have row reduced, fully row reduced this matrix because every row has a leading 1. And voila, we have the solution. x is -1, y is 3, and z is 3. So note that this is considered a one single solution because x and y and z is a particular number. So this is not three solutions. So now hopefully you have sort of understand how this process go. Again, don't get too stressed if you don't understand it all yet. Try a practice problem and see if you understand it. If not, rewatch it and make sure you practice. So same way as two equation with two unknowns, here we have special cases with infinite solutions and no solutions. So here we have a special case number 1, which is infinite solution with two arbitrary variables. So what are arbitrary variables? Here I'm going to explain. So let's look at this system of equation, and I'm going to represent it in the matrix form. First off, you might already notice that second equation and third equation is simply some multiples of the first equation. But let's say you didn't notice that and you follow through with your regular row reduction, which to clear the 2, multiply by -2 and clear the -5 by multiplying by 5. We're going to see these two rows comes out to be row full of zeros. A row full of zeros is eliminated from system because the equation simply reads 0x plus 0y plus 0z equals 0. And that's not saying anything. Now you are actually fully row reduced because row 1 has a leading one, and this is the only row that there is. So you're row reduced. So if we just look at this equation says x plus y plus z equals 5. So we have the fixed variable being the one with the leading one. And then the variable without a leading one are arbitrary variables. So arbitrary means that they can be anything. And for the arbitrary variable, we're going to represent it like this. So here's what it means for x and y to be arbitrary, and they can be anything. So this there's only one equation here, but we have three different variables. So basically, you can give me any x, you can give me any y and z. I can give you an x that will satisfy this equation. So that's what it means for y and z to be able to be anything. So again, this equation read x plus y plus z equals 5. So let's say you give me y equals 1, z equals 1. Then I can give you x equals 3, and this equation will work. Or you can give me y equals 2 or z equals 2, then I give you x equals 1, and this equation will also work. So that's why there are infinite number of variables, and 2 of them are arbitrary because 2 of them you can give me anything, and I can make this equation work. So again, y equals y, z equals z to represent the arbitrary. And here we will rearrange this equation to give us the solution for x, which is 5 minus y minus z. So here's what the final answer is going to look like. And this is exactly the WebWork format and the test format. So here's how you're going to write it out. And this is the solution with two arbitrary variables. Another special case is you can have infinite solution with only one arbitrary variable. So let's look at this system, which is already fully row reduced. Again, we have the fixed variable being the variables with the leading ones in the column, and the arbitrary variable being the column without a leading one. So here x and z are fixed and y is arbitrary. So if we decipher the two equations, here's what they are. Again, y is the arbitrary, so y equals y. And we already had that z equals 2. And we're going to rearrange that first equation to get x equals 4 minus 2y. So this is the final solution. And this is a solution with one arbitrary variable with infinite solutions. Here we have another case which has no solution. Let's look at the system of equation. And we'll proceed with our usual reduction method. Here I'm going to try to get a leading one for row 1 by getting rid of this 2. And I do so by multiplying row 1 by negative 2. Add these two rows side by side. And I realize that the row 2 has become a row with 0, 0, 0, and some constant on the right. Now, if you read this equation, it says 0x plus 0y plus 0z equals 1. Well, a bunch of 0 can't add up to 1. So if you reduce a matrix and arrive at some row that says 0 equals some constant, then there is no solution to the system. And when you come out with a row like this, you can immediately stop and say that there's no solution, and you're finished with the problem.